Okay, what is the definition of the heat of reactions, heat of formation, and also heat of combustions? Um, Generally for the heat of reaction is uh, yeah, we know that heat is either absorbed or released, right? Or removed from the system, okay, from the chemical reactor, okay. So we want to keep it at the substance at the same temperature, okay. So just remember that heat is either evolved or absorbed lah, okay. When 1 mole of the product is formed at the constant pressure, so that is a heat of reaction. Um, for the heat of formation actually is a heat whether we added or remove, evolve or absorb, okay, during formation of 1 mole of substance, okay, from its component element, okay. So this is generally we measure at the standard condition lah, 25 degrees C, if I'm not mistaken, 25 degrees C and 1 bar, okay. You have to remember 1 bar, okay, not 1 atm. Okay, we use that standard condition. Okay, and then heat of combustion, of course, is related with the oxygen. Okay, need the complete combustion with the oxygen. Okay, must be conducted at the under uh, the heats or the energy lah released as a heat. Okay, because it's combustion, right? When you combust, heat gonna be released lah. Okay, so the direction is gonna be complete combustion with this O2 lah. Okay, so we measure under standard condition lah. Okay, so completely combustion meaning that is a complete burn. Okay, generally if pyrolysis or combustions, they use this. If you know what is different pyrolysis, there's a pyrolysis, combustion, gasifications. This is related with the heat release because we heat it. Okay. So what is the difference between pyrolysis, combustion, and gasifications? Combustion is with oxygen. Okay. Pyrolysis is with the limiting oxygen or not oxygen. Okay, when you heat it. Okay. Gasifications, sometimes they use a two-stage. Okay, pyrolysis is a part of the gasification sometimes. Okay, and the target of combustion, the product is the gas. Okay, rather than liquid combustion. Okay, but pyrolysis is many type of the pyrolysis, whether slow, fast, or flash. If slow, our target is generally some the solid. Okay, and then for liquid is we use a flash and also fast pyrolysis lah. It's depending on the heating rate actually. Okay. Let's see the standard heat operations. Okay. Previously we never consider about the chemical process. Okay, we just consider the physical process, right? Okay, latent heat, right? Is just physical. There's no reactions. Sensible heat, change in the temperature, change in the phase, but no chemical reactions, right? Okay. So generally, chemical process is together accompanied by the transfer of the heat and also temperature change lah. Okay. So during the when you draw the hypothetical part, there will be the heat of reactions. So please remember. Okay. So if you look at here that most of the heat effect of the chemical reaction is calculated in the standard way. So there is a standard condition. Okay. And heat of specific reaction depends on the temperature of both and reactant. So if A plus B equal to C plus D, there's a reactant and also product. So that one is the stoichiometry should you have to remember whether you want to use positive or negative for the heat of reaction. Okay. So for example, for the process, um, we have reactants, right? A1 and A2 lah. Or sometimes generally we use A plus B, AB, right? And outlet is B, CD. Okay, but this one is I'm using A1, A2, and A3, A4 lah as a product. So this one is heat release or absorb. Okay. So if heat release is exothermic and if need the heats or we want to absorb, we use negative lah, that enthalpy, change in enthalpy. Okay. So meaning that negative heat release, positive uh, absorb. Okay. The calculation of the change of enthalpy is important for the further calculation of Gibbs energy and also entropy, because we want to know that whether your Your system is in equilibrium or not in equilibrium, right? Because generally for the what is it? Reversible process. Okay. Okay. So for the steady state open system with the stoichiometric reactions, this is using V1, V1. This is a stoichiometry. Okay, V3, V4. So we times with the stoichiometry, and this is summation of the Q is summation of stoichiometry times with the enthalpy. You have to remember I is for each species, meaning that a reactant and also um, products. Okay. So Q release or absorb is identical of the enthalpy change. You have to remember. So this is what we call it as a heat operation because it's already involving the chemical process. Okay. So what is a standard state? If you look at here that define what is the enthalpy change. If you look at here that enthalpy change from the stoichiometric reactions when the reactant entering a standard state. If you look at here, the pressure is 1 bar, not 1 atm. Okay, please remember, this is we specify for the gas, liquid, and also solid. All the standard state at 1 bar. Okay, so if you want to rewrite the energy balance at the standard state, okay, so meaning that HI for the species not is a standard. There's a denote here. You have to remember that. Okay, you know already, right? Okay, sometimes we use if at 25 degrees C, H naught 298. Okay, the bottom part is the subscript. Superscript is not, and subscript is 298. Okay, at 298 degrees C. Okay, and the standard state. Okay, gases. Okay, 1 bar Cp naught equal to Cpig. You have to remember this one because it's a 1 bar. Y naught is equal to Ig because it's at a low pressure and low temperature. Okay, low pressure, like especially low pressure because 1 bar. Liquid and solid for also 1 bar. Okay, Cp naught. Okay, there's a knot. Okay, over there. Okay, so all conditions for the standard state are fixed except the temperature. Okay. So this is an example of the how to use the stoichiometry for the calculations. Okay, if the stoichiometric coefficient is doubles, meaning that the heat of reaction is the double. Okay, so if you look at here for the hydrogen, right? Okay, for the production of methane hydrogen. Okay, so meaning that we have to look at here that if based on the hydrogen and nitrogen, so we have to this one. Okay, times or divide with the stoichiometry. Okay, it's depending on the stoichiometry. Okay, okay. So I think all of you know this one. Okay. Uh, okay. So since there are many reference tabulated for delta H 298 degree for the commonly formed reactions, but sometimes this is not practical, very limiting data, right? Not all reaction can take place at 298 Kelvin. Okay. So how to calculate of the heat of reactions? This is what I told you previously that you have to use heat of the formations. Okay. So uh, to calculate the heat of reactions by using the heat of formations. Okay. So you have to refer to the appendix. Okay. Standard heat, standard enthalpy and skip energy of the formations at 298 Kelvin. Right. 1 bar. So it's given, I think, in appendix C or appendix D lah. Okay, so you have to refer that one. Okay, C4 or D4. Okay, or B4. So you can see here that is a heat capacity for the solid, heat capacity for the liquid, and C4. C4 is a standard enthalpy and Gibbs energy. So it's given for the delta H of formation and also delta Gibbs energy at the standard conditions. Both okay, for the calculation. Generally, if you calculate by using hypothetical part, we will calculate the entropy as well as the enthalpy lah. Both then. Okay. So the symbol actually we put here delta F298 for the species I. Okay, whether reactant or the product. H naught is a standard condition. So you have to remember that one. Okay. So I hope that you familiar with the heat of formations. Most of the reaction we use this table. Okay, if not available in the main textbook, So you have to refer to another reference, okay, to determine the heat of formation, and finally you can use it for the heat of reactions. Okay, look at the heat of formations. Okay, a reaction will form a single compound from its constituent element, meaning that from the reactants. Okay, the reactant, this one is the constituent element. The element is CO. That is the element. Okay, so if you look at here, that the formation of the methanols from carbon, oxygen, and also hydrogens. Okay, so as I uh, explained the definition, right? It's based on 1 mole of the compound form. Okay, from the component elements. Okay, the heat of formation is based on 1 mole of the compound form. Okay, from its element. This one. Okay. So standard heat formations, if you look at here, the symbol, standard value, heat of formation F, and also absolute value temperature. Okay, so how to calculate, for example, this one, how to calculate the heat of reaction, like for the water gas shift reactions. If you look at here, that table C4, right, for the CO2, if you refer there, delta H formation 298 carbon monoxide, carbon dioxide, right? Carbon dioxide. Okay, negative 39351. Okay, so this one is given already in the tables, right? CO and also H2O. But zero is for the hydrogen is due to the element. Okay, oxygen, that is a element. We didn't include for the heat of formations. Okay, element is zero. Okay, so how to calculate? If you still remember, right? So we have to cancel out these equations to get the full equations. Okay, so from that one, right, okay. So the for water gas shift actually is this is the full equations, because in order to get the heat of formation, heat of reaction of the water gas shift reaction, we need the heat of formations. Okay, this is the formation of CO2, CO, and also H2O. Okay, from this one, just cancel out this one, right? Cancel out. So we can get this one, the total equation. Okay, and just sum up this one. Okay, so if you look at here, that stoichiometry for this one is -1. This one -1, this one is 1, and also 1. Okay, so hydrogen is 0. This one is CO2, 1, and also 1. Okay, so you can get the value for the heat of reaction at standard condition. Okay, so if the reaction enter at 200 degrees C, so what you have to do is you have to consider, so you have to bring it that the condition to the standard condition, 200 to the 200 degrees C to 25 degrees C lah, at 1 bar. Okay, and then at the standard conditions, you have to calculate heat of reactions. If you still remember when you learn at the uh, mass and energy balance class. Okay, okay, is it clear? Okay, let's see the example of to calculate the standard heat of standard heat. This one was it for the HCl plus O2, right? Okay. Um, HCl plus O2, and then H2O plus 2Cl. Okay. So standard heats of formations, if you look at here, the HCl is 92, and H2O is this one. This one element equal to 0. Okay. So if you look at here, that just rearrange the equation, the formation of the HCl and also the formation of H2O. This is a water vapor or steam gas, right? This formation. So just cancel out this one, and you can get 2Cl, this one, this one, this one, and this one, right? Okay, so just time is 4 because it's a 4 mole of stoichiometry lah. And then it's 2 lah, this one, H2O, 2 times with 2. Because if you still remember, if a double of the stoichiometry, the heat of reaction is going to be double. Okay, so we can get 114,408. Okay, Okay, any questions? Heat of reactions, I think is clear. Is it okay? Okay, let's we move to the heat of combustion. Okay, now already explained the heat of reactions, heat of formation, and also heat. Now is heat of combustion. Actually, it's similar. Okay, commonly encountered as I told you that element or compound with the oxygen. Okay, to form specified combustion products. Combustion, if you pyrolyze or you combust the biomass, uh, they will produce like a gas, solid, and also liquid. Some simply like that, or other substance or other compounds. Okay, so whether it's vapor or liquid, if you do the condensations, the vapor will be condensed and produce the liquid. Okay. Okay, data always 1 mole of substance burn. Okay, please remember that one. Okay, let's see the example of the formation of the butane. Okay, this is I think if you look at here that is similar, right? Okay, heat of formation of the CO2 because this is butane, right? So we have no data for this one. Even from the your main textbooks, we don't have this data. So first, what we have to do is the formation of CO2 and then H2O and also this one. So this one we can cancel out this one, right? So just make it as a full reactions and you can calculate. This is formation 4. This is 4, right? And this is a 5. This one is 4. So you can get this is 1 because this is 1. Okay. So you can get the answer. Okay. Similar like a heat of reactions. Okay. We need the data of the heat of formation. Okay. Tutorial 5. Okay. Let's see this one. What is the standard heat of combustion of N-pentane? What's the tutorial 5? Okay. If the combustion product are H2O and CO2. Okay. Let's see this one. I share. Uh, I share the Jamboard. Okay, go to the Jamboard. Easy. And now I explain. Okay. What is the standard heat of combustions of the N-pentane gas at 25 degrees C in the combustion products? Okay. So what you have to do is you have to write the equations, right? So N C 5 H12. Okay, plus O2. Okay, CO2 plus H2O. Okay. Uh, so what is the standard heat combustion? Delta H. Anyone can calculate standard heat because it's a standard condition. Okay. So if you look at here that delta H, okay, not C equal to summation VI delta H F I. Eh, this one is not. Okay, so please calculate. Okay, you already learned. This refer to the table C4. Can you calculate? Look at the fractions and then calculate. What is the standard heat of the C5H? Okay, oxygen and also H2O. Okay, good. Ada punya identify. Okay. So please calculate. Give me the answer. Give me the answer. Okay, give me the standard heat of formation for this one. Number one. Okay. Number one, two, three, ish, and four. One, two, three, four. Okay, you can put okay. 146.76. Okay, negative. Two. Two is zero lah. Okay, two is zero. This one is zero. No need to put 393.150. Okay. So if you look at here, there's a stoichiometry here. Right. Okay, so please time 5 and also 6. The previously we add all the what is it? Heat of formation, right? But you also can use, if you learn in energy balance, you use a product minus with the what is it? The reactance is similar. Okay, it's up to you. 285 kilojoule per mole. Okay, let's go. Please calculate. Give me the answer. What's the answer? Final answer. 353. Okay, good. Okay, good, good. Thank you. Okay, done. Okay, good, good. Thank you very much. That's the answer. Uh, let's we continue. Okay, okay. So that's good. I don't think total six you is similar lah. Okay. And if you want to do the answer is this one. The answer is negative 92 to 0 joule. Okay. And this one is negative 905 or 68. Yeah. Okay. That's the answer. It's similar lah. Okay. I don't think we're gonna proceed with this one. It's just easy, easy. Right. Okay. We've moved to the temperature dependent of delta H. Is we almost finished? Okay. Okay, okay. Delta H, temperature dependent. Okay. So this is the one of the important part after you learn about the heat, latent heat, sensible heat, latent heat, heat of reaction, heat of formation, and also heat conversions. So we see the dependent of the temperature. As I told you that the reaction is doesn't mean it's occur at very low temperature or pressure. Okay. So most of the reaction in industry occur at the temperature other than the steady state. You have to remember that one. Okay. Even if in the lab I do my experiments, my reactions, because my research is about the pyrolysis, so the reaction is more than 400. 400. If torrefactions, the temperature is going to be around 200. Okay, so it's high temperature. Okay, if high temperature, the some is going to be proportional with the pressure, right? Okay, it's going to increase the pressure. Okay. So example, the reactant is enter the reactor at 200 degrees C and the product exit at 200 degrees C, or maybe it's a little bit low or maybe a little bit high. So the standard of reaction is delta H, not 473.15 Kelvin. So you have to calculate at 200 degrees C. Okay. What we have to do is you have to use a hypothetical part. Okay. You still remember how to use this hypothetical part? So I hope that you still remember this one. Okay, how to use this hypothetical part. Okay. For examples, the hypothetical part is this is the convenient way how to calculate the change in the enthalpy, because there is no information from the database of from the reference the heat of reaction at 200 degrees C or maybe 300 degrees C. So what you have to do is you have to bring the what to say the calculation, okay, or system to the standard conditions, meaning that from 473.15 Kelvin to 100 degrees C, okay, bring it into standard condition. Okay, this is a delta H not lah. I just use that using a delta H not lah here. Okay, delta heat of reaction. Uh, reactions lah. Okay, or that delta H, a standard heat. Okay, at the standard conditions lah. Okay, and then this one is delta H product and also delta H reactants. If there is a change in the temperature or change in the phase for the system, okay, so you have to combine this hypothetical part. Okay, maybe change in the temperature or change in the system first, maybe from the liquid to the gas, right? Okay, and then gas to the standard state lah. Okay, this is standard state 1. Okay, so you have to calculate if change in the temperature sensible change in the phase. Change in the phase is going to be latent heat, and change in the temperature is going to be heat of the sensible lah. Okay, and then standard heat. Okay, similarly also, if for the gas, and then you want to your product in the liquid, right? Because this is in gas. Okay, and also in gas standard too. But if you want to bring it to the liquid, also is possible. Okay, and make it into the liquid lah. Okay, because there is a two-phase system. Okay, there's a change in the change in the phase and then change in the temperature. You have to consider. Then you can calculate delta H. Hypothetical part is important. If you how to say, if you're not familiar or not master with this hypothetical part, I don't think so you can calculate any problem after this. Okay, so and just combine delta H reactants plus delta H 290 delta H naught. I just use delta H naught and then delta H product. Okay. Okay. So to calculate the standard heat operations, similarly, I already told you, you have to consider the stoichiometry. Okay, negative and positive. For the negative is for the reactants and positive for the products lah. Okay, I think you're familiar with the reactions. And this is also the what is it? The convention or the symbols lah. Okay. I is for the element at the standard state. We equal to not lah. Okay. I don't think this one. Okay. So this is the standard state of the enthalpy of the elements. Okay. This is already explained actually. 1 mole of compound AI, right, from the element of E. Okay. So for the element is equal to 0. Okay. So you have to remember that. Okay. Delta HVE is the element. Okay. So if non-standard heat operations, so you have to use heat of formation to calculate standard heat of operation. Okay, so look at this one. Example berapa ni? Which example is one? I cannot see. Oh, example 7. Calculate the standard heat 25 degrees C for the following reactions. Okay. I think this one already explained how to calculate. Okay, based on the heat of formations. So the product is minus with the products 2 more, right? Because this is element. This is element. So product is minus with the reactants lah. Okay, and you can get this one. So please find with the stoichiometry. Okay, whether you want to plus or minus is up to you. It's a similar. Okay, but generally we use this method lah. Product minus with the product minus with the reactants, right? Okay. Okay. Yang ni apa ni? Okay. This one I already explained or not? Not yet. Okay. Heat of reaction. Okay. Since the calculation of the what is it heat of reactions lah. Actually, we need the information of the CP. Okay, because delta H equal to CP dt, right? Okay, but that one is if T2 minus T1 is for the low temperature and also low pressure. But this one, if the reaction is occur at high temperature or high pressure, so we need the special equations. Okay, so we need also delta Cp lah. Okay, since previously is only one not one elements, one components, right? Okay, but when involving the reactions, so it's going to be another I elements, okay, or I components, I compounds lah. Okay, so how can we combine this A plus B equal to C plus D? Okay, previously in chapter which one? Sensible heat. Okay, we just use the, if you still remember, right? They have a integration and mean head capacity. That one is only for one component because there's the narration. Okay, you still remember, right? It's involving the parameter of the constant of A, B, C, and also D, right? Okay, summation, integration of CP dt. Okay, A T naught plus B divided by 2. Okay, T naught power of 2. If you still remember that. But that one is only for one component. Okay, but now uh it's involving the chemical reaction. So there's a many, there's a reactant and also product. So how can we calculate that one, right? Okay, similar, it's a similar equations, only they have additionals. Okay, if you look at here, that CP, there is a what is it? Delta CP. Actually is a summation of CP of all elements. Okay, product and also reactants lah. If you look at here, that I lah, this one. Yeah, CP. So means summation lah. Okay, later I will show you. Similarly also for delta H lah. Okay, A, B, C, D also similar. The constant. Okay, we use delta A. Delta A. Previously we use A, right? Okay, delta B, delta C, and delta D. Okay. 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 So if you look at here, once you determines delta CP, delta A, B, D, right? So just substitute into these equations. Okay. For the calculation of the heat of reactions, right? This one. Okay. So you need delta H naught. Okay. Delta H naught is we can refer at this one later. From the heat of formation. Okay. Plus with this one. This is the important one. This one. Okay. The integration and the mean heat capacity lah. So what is delta Cp? This is delta Cp. Okay. So if you look at here, that delta A T naught tau minus 1 lah. Okay. Delta B, delta C, and also delta D. This is another equation. Very important equations. Generally, we will calculate as IDCPH. Okay. T naught T, the A, DB, D is the delta. Okay. This is in mathematical form. So delta S is a summation of VI stoichiometry for each element, reactants, and also products. Okay, plus reactant plus with the products. Okay, so AI for each. So A, B, C, and D, please refer to appendix. If you look at there, previously I already mentioned in appendix C1, right? Okay, appendix C is important. Okay, similarly also you have to use for B, C, and also D. Okay. So in terms of mean head capacity, this is mean head capacity lah. Okay. So the difference is only here. Right here. Right. Whether you want to calculate by using mean head capacity of integrations, it's up to you. The answer is going to be same. Okay. But generally, if you use a head cap, if you still remember, there is a case 1 and also case 2, right? For the calculation using mean heat capacity, we want to find the, what is it? The final temperature, right? Okay. So you can use mean heat capacity. But if you want to use this equation to calculate the delta H, also possible. Okay, so it's similar with this equation. This is in terms of integration, and this one is in terms of mean heat capacity lah. So expressed in heat capacity. Okay, in summary, if you look at here that to calculate the heat of reactions, right? This one is for by using integration, and this one is in terms of the mean heat capacity. So actually we can summarize delta H naught. This is a bit generally, this one if we refer as 298 298 Kelvin. 298 Kelvin, because also zero. Some book they use 0, some book is using 298. So it's similar. Okay. So this one is integration, and this one is mean heat capacity. So for the actual equation, please refer to the previous this one. Also, they you can refer to the main textbook. Okay, integration form, integral, and also mean heat capacity form. Okay, this is important. You have to highlight this equation. Okay, let's see the example 8. Okay, how to calculate this one. Later we do the tutorials. Okay. Ada tutorial dah. Okay. Calculate the standard heat of the methanol synthesis reaction at 800 degrees C. CO2 in gas form. Okay. The system in the gas form. Okay. Plus 2H2 equal to methanol. So H naught, how to determine the H naught? Please refer to the how to calculate from the heat of formations. So if you look at here that this is element, if you find it from the table C4, right, CH3 OH, CH3OH. What is it? This one, methanol, right? So for the methanol is 238. No. 200. Okay. This one times with -1 minus minus this one. Okay. Also one CO2. So you can get this one. Okay. So you already have this one. This one. Okay. This one. You have this one already. And also this one. Okay. So evaluation of the parameter. Okay, if you look at here that stoichiometry is 1 for the methanol and -1, -1. Okay. So just determine the parameter from the table C1, A, B, C, and also D. So if you look at here that this is 6, 3, 6, and also -5, right? But once you convert it into value, okay, this one is actually 12.216 times -3. Okay, please remember this one. This is -3, this one -6, this is 5. But in the table, they write it in the opposite. Okay, please remember that. And then summation, for example, for A, times with the stoichiometry for A, methanol, hydrogen, and also, what is it? Methanol, hydrogen, and CO2, right? Okay, so summations, you can get A, A, B, and also C. Okay. So use the integration equation, or you want to use the mean heat capacity. So you will get this mean heat capacity. Please times with this one, okay? R constant. Please remember. Okay. So after you times with R, you can get the similar unit with the H naught in joule. Okay. So after that, just summation. This one, see? Times with R and the integral part. So you can get delta H naught. Okay. Okay. Can you do this one? I'll give you around 10 minutes. Okay, similar step like this one. Okay. Please calculate nitrogen plus H2 equal to NH3 lah. So if you look at here, what you have to do, the equation is, what's the equation? Delta H, right? Delta H not equal to K plus, you want to use MCPDT or integration? Okay. R, if you want to use integration. R T E naught delta CP not divided by R dt. Okay, so please determine this one. Look at here, this is the element, this one element. Okay, just times with NH3. 2 times with the NH3, delta H1. So what is the delta H naught for the ammonia? Okay, that is a first step. The second step is you have to determine the parameters, delta A, delta B, delta C, and delta D. So if you look at that, right? So just construct the tables. Okay. Construct the table. Then okay. So use this one. So this one is VI. This one is A. V, C, D. Right. Okay, this one is I. Starting this one NH3. Just put it here. Okay, N2, H2. Okay. This one is times with 3. This one is times with 6. -5. Okay. And then summation of delta A. Oh, okay. Okay. And then summation of delta A, delta B, delta C, delta D. Okay. Please determine this one. Okay. And then substitute into IDCPH lah. So IDCPH just now is what is it? This one. T not. Okay, delta CP. Substitute into this equation. Okay. So anyone delta H, please calculate. I give you around 10 minutes. Give me delta H 298. Anyone? Okay, 9 negative 92220 joule. Okay, good. Okay. So please calculate total H operation. Written. Either one you want to use mean heat capacity or integral is up to you. Please calculate. Okay. So you determine already the delta H, right? This one. This one, right? Okay. So you need to determine this one. And times with R. So you can get delta H. So to determine the integration of the CP, this is this one. Okay. Or you want to use mean heat capacity, you use this one. Please calculate. Okay, what's the answer? Oh, Nur Umairah. Nur Umairah. Ada kat situ tak? Are you there? Nur Umairah. Ada situ. Nurul Maira. Tengah kira. Who's that? Vanessa. Yunan. Vanessa. Counting. Okay. So B is going to be the same. Okay, B is going to be the same. A similar method, similar procedure, similar step. So just refer to the previous example and also the tutorial that you done for 7A. So for the B, you can, I think you can calculate. Okay. Okay. Lama ni. Uh, Vanessa dah. Oh, anyone? Give me the answer. Syamsul Zaman. Any answer? Syamsul Zaman.
Cik ayat tu.
Tak siap lagi. Lama. Okay. So later I will explain the until example 9, right? And then for the next class, we will do you have to do this tutorial first. Okay. And then we will discuss in the next class. So just a brief discussion, the step, but you have to do first this tutorial 8 and 9 later. Okay. Okay, let's see. What's the 273? Eh, 273. Why you got that one? Later you check. I got this one. Negative. Yes, 1 1. Almost 1 1. I got this one. 109,795. Yeah, please check. Okay. So please remember that this one you have to times with R, okay? CP. Once you calculate CP, you have to times with R and plus with the delta H not. Okay. So this is my answer. 1154. Oh juga. Okay. So okay, I'm not sure. You have to recheck, recalculate. Okay, the answer, or maybe I'm the one who gave a wrong answer. But I try both methods by using the mean head capacity and also uh, this one integration. So I got this one, this number, this value. Okay, so please recalculate. If I'm wrong, please do let me know. Okay, so we continue a very uh, short part on the what is it, on the heat effect on in the industrial process. Okay. Uh, okay. As I told you that for the industrial process, the reaction is not occur at a very low temperature, right? Okay, for the industry and high temperature, maybe high pressure, not the similar stoichiometry. What else? Uh, uh, It's not the inert. Maybe there's some there's gonna be excess excess reactants like you use excess air or excess nitrogen, right? Whether you consider is nitrogen involved in reaction or not. So all those things you have to consider lah during the reaction, especially if there is air enter the reactions. Okay. So if you look at here that reaction industry is rarely occur at 25 1 bar. Okay, and the reactant is always the excess component, even for example, like the biodiesel production, like from the vegetable oils. Okay, react with the fatty acid react with the methanols. Okay, so to react with the alcohol, generally alcohol is based on the equations, 3 mole of the methanols used to react with the fatty acid of the vegetable oils to produce biodiesel. But there's a reversible reaction, so we need the excess of methanol so that your reaction can shift towards the products to the right side of the equation rather than is reversible to the left equations, right? So that is important. And the conversions, there's no 100 conversions. Okay, not always complete. Sometimes it's 85 conversion, even the it can be reached around 90 or 95%, but it's not never reach a 100% conversion. And reaction is took more than one place simultaneously. Sometimes it's parallel reactions. Okay, series reactions, so that one is you have to consider. And also temperature inlet is not equal to outlet, and involving the inert materials generally is nitrogen. Okay, so that is the reaction industry. So what you have to do is by applying the method of the what is it, hypothetical part, as well as you learn about the sensible heat, latent heat, so you can apply to calculate the heat in or the heat involving in the reaction in the industry. Okay, for example, this one, example 9, if you have a main textbook, I just explain this first. Okay, I just explain this first briefly. Okay, and then you have to do the tutorial first, this one, tutorial 8. Okay, I want you do this one first. I will explain a little bit. Okay, I think all of you have my lecture note, right? So please do this one first. I will explain a little bit, and then in the next class, during 1 hour of class, I will explain tutorial 8 and also tutorials 9. Eh? So you do this one, A and B. It doesn't matter, 50% don't need to do because it's similar 25% and 50%, and also tutorial 9. So we will discuss together. Similarly, just like a previous one. Okay, I give you the Jamboard and give me the answer. Okay. So this is a task. Okay. So if you look at here that for the example 9, what is the maximum temperature that can be reached by the combustion of methane with 20% excess air, both the methane and the air enter the burner? 25 degrees C. You have to remember that when we deal with the determination of the maximum temperature, meaning that the final temperature, you have to recall it back. You have to use there's a two cases, right? First cases and second cases. So you have to use the method of the second cases. We need to do the iteration process, right? Okay, that is the important, and is involving the 20% of the excess air. Okay, there is the directions. Okay, when there is a combustion of methane, of course, it involving the methane and also oxygen. Plus, there is the excess air, nitrogen and also oxygen, right, to produce uh, CO2, water, and also nitrogen is going to be not react. Okay, so if you look at here, right, normally that direction is CH4. This is normal, right? But when there is a 20% excess, okay, when there is a what is it? What we call it as air enter, right? Air contain of 70% of the nitrogen and 25% of oxygen. Okay, so when there is an excess, okay, this is 2 more times with 2 more. So when there is excess, meaning that it's become 120%, because 100% react with the methane, right? For the 2 more. 2 more is react when with 1 mole of the methane. But when there is an excess of the air, it should be it become 120% or 1.2 more. Okay, times with 2. Okay, times with 2. Okay, so this is you have to remember. Okay, and produce CO2, water. Similarly, this is for the nitrogen. Nitrogen is a methane, but for the oxygen is because it's completely react 100%, and the rest is 20%. So they leave as unreacted compound. So it's going to be 20% or 0.2. So you have to remember this one. Okay, if no excess of the air 100%, so meaning that this is the equation. This is the equation. But there is excess, you have to make it into 120% or 1.2, the ratio. Okay, so basis of the calculation, if you look at here that you have to do the hypothetical part. Okay, so if you look at here that from this one, we enter at 25, isn't it? We enter at 25, right? Yeah, 25 degrees C. And we have to define the final conditions, the temperature at the final condition. So meaning that you enter at 25, right? You enter at 25, bring it to the second condition of finals, and bring it to the final temperature. So you can get, we consider as delta H equal to 0, this one. Okay. Everything you want to find the final temperature, we have to consider that delta H equal to 0 as a total. Okay. So we have to calculate the basis of the calculation, 1 mole of CH4. So when enter is 1 mole of CH4, 2.4 and 9.02 from this calculation. If you look at here, 2 times with 2, this one 2.4, this one is 1 mole because the basis is 1 mole of methane, meaning that similar with the stoichiometry. Okay, and this one is a 9 and exit to 1, this one you have to calculate. Yeah, because you have to include in this one. If you look at here that when you calculate by using the temperature dependence of the equations, right? You have to remember, you have to use this one, this one. Okay. So this is the number of mole. Q equal to delta H maximum when Q equal to 0. Okay, there's no heat loss anymore. Okay, so this is the finals, and by using the hypothetical parts from the reactants, okay, you have to do this hypothetical part actually. Okay, because you have a general view how to calculate the Q and also the final temperature. So you use this information, right? Okay. So energy balance is going to be delta H 298 because plus delta HP. There's a no reactant. Why no reactant? If you look at here, that enter at 198. Only the product, right? Okay, that is the product. So just calculate the delta H, this one, right? This is by using heat of formations, so you can get this one, right? And then the most important thing is delta HP. Okay, this is the delta H, this one lah. Delta H 298, this one. This one. And then you have to calculate delta H, HP. This one, you have to calculate. You have to determine A, B, C, and also D lah. C is equal to 0, this one. Okay. And then substitute into delta HP lah. This one. Right. Okay, delta HP. Because tau is equal to T divided by T naught, okay? Tau. You still remember, right? So we use this mean heat capacity equation, right? Okay. And then you have to calculate delta HT. This one you get a delta H naught, right? And then this one mean heat capacity. Okay, just substitute, rearrange this question, express in terms of T2. Okay, so and then you can guess a value of T2. Okay, any value generally is more than T naught lah, because when enter at 25, so just guess around 100 or 200, 300, 500. It's any value, so it doesn't matter. Okay, once you determine T divided by T naught. Okay, for example, this one is 298, right? Because enter, and maybe this one is 1000 Kelvin. Okay, and do the iteration. This one. Okay, do the iteration, express in terms of T2. This one I do by using the Excel. Okay, so when I do my, I guess the starting temperature, because I start with the 298. Okay, 298. 298 Kelvin. I start with 298 Kelvin. And then I got this one, new value. And this one I enter new value. Yeah. When I enter 200, dia kan, T1 lah. T divided by T naught. T divided by T naught lah. Right. So it is meaning that T divided by T naught, I guess tau as equal to 1. And then I got new T2 lah. Okay. And then T2, I got this one T naught, T2 lah. T2 divided by T naught. T naught. So this one, right? So just substitute to this one. I got this one, this one, until I convert this one. So this is I consider as a conversion. Okay, so I got this one 2066. Okay, after how many iterations? 5, 4 or 5. Okay, okay, is it clear for this example? Is it clear? Any questions before we stop? I guess everybody clear with my explanations. Okay, what you have to do is your assignments, okay, your task is calculate the theoretical flame temperature when ethylene at 25 degrees C. Okay, is a similar, okay, similar step as this one. Okay, okay, for test or final is going to be like this one. It's combination of sensible latent heat, heat of reaction. Heat of reaction is including the heat combustion is similar lah, but using a heat of formation. Okay, and then this is a calculation of enthalpy, but for the next topics, you have to calculate also delta G and delta S, the entropy. Okay, okay, so you do this one A and B, first with the theoretical amount. meaning that 100% 1 plus 1 lah. No, 1 ratio is 1 1 lah. This one is calculate ethylene. Ethylene meaning that C2H4 plus oxygen, okay, equal to CO2 plus H2O. And then 25% of excess air, 25. When excess, you use this one. It's a similar step. Okay, just follow this one and then you can calculate. Okay, and then tutorial 9. Okay, what you have to do is similar also. Okay. What is it? Ammonia mixed with 30% more dry air. This one is excess. Nitric oxide, the gas enter the reactor 75 degrees C, conversion is 80%. Okay, conversion 80%. Okay, if conversion 80%, meaning that NH3, right, ammonia is only react 80%. Everything is converted 80%. Okay, faham eh? And then the rest is gonna be become a product also. Okay, because there's still 20% of the NH3. Okay. If no side reaction occur and if the reactor operate adiabatic, delta Q equal to 0 lah. Okay, you have to remember what is the temperature of gases leaving the reactor. Similarly, also you have to do iteration. Please do first, and then in the next class, I will explain and we will discuss. I want to know the answer. Okay, wrong or right, it doesn't matter. But I want to know I want you to practice. Yeah, any questions?